Hey folks, welcome to Solutions. We're going to be talking about a bunch of different types of solutions. This is the introduction. There are a lot of different terms, so please have your notes ready. You're going to be writing down a lot of terms, a lot of definitions, so prepare to pause the video a few times so you can write down definitions. Right. What is a solution? Think of some examples of a solution. You all know what solutions are. Think of what might be dissolved in what. Alright, I'm sure you came up with some examples, stuff like salt water, for example, or Kool-Aid, or all sorts of things like that. So you can come up with a bunch of different examples. We have a couple of terms. We'll define these in a minute, solvent and solute. The solvent is the thing that is doing the dissolving. The solute is being dissolved in it. So if we look over here, this is salt and water. The salt is the solute, and it's being dissolved in the water. Alright, and over here, we have some food coloring being dissolved in water, and over here we got a bunch of other stuff being dissolved in water. Specifically what I want to focus on is the carbon dioxide that's dissolved in the water. So in these three cases, we have liquid as the solvent, water specifically, which is doing the dissolving, and over here we have a solid that's being dissolved, the salt. Over here we have a liquid that's being dissolved, which is the food coloring, and over here, sure, we've got color and all that kind of thing, but we also have a gas, which is carbon dioxide, and carbon dioxide has been dissolved in the water as well. So we also have other things which you typically might not think of as solutions, but they are solutions. For example, a wedding ring, which is made not out of pure gold, but out of gold and silver and some other metals potentially. So a gold wedding ring is actually a solution. It's actually made up of multiple things. If you look at a trumpet is made of brass, and brass is a bunch of different metals put together, including copper and other stuff. And down here we have a sink that's made out of stainless steel. Stainless steel is not just iron. Iron rusts, and so they add chromium and other metals to it to make stainless steel. So we can have solids dissolving in other solids. Similarly, we can look at gases. And we can have gases dissolved in other gases. And the gases that you and I are breathing, nitrogen is the largest component of the gas that we have. Nitrogen is like 75% of air, give or take a little bit. So it is the solvent, and there's other stuff like oxygen, carbon dioxide, and other stuff that's dissolved in our air. So it is, again, a mixture. So let's think for a moment about what a solution is. You might want to pause the video and write some of these things down. In fact, write all of them down. A solution is a homogeneous mixture. What does homogeneous mean? That's right, you can't see different things in it. Just like the air, you can't see different things in it. In Dr. Pepper, it just looks like a continuous color. You can't see the different things in it. So it consists of one or more solutes dissolved in a solvent. Right? And as I said earlier, the solvent is the thing doing the dissolving. It might, for example, be water, which is very common when we think of solutions. We tend to think of things dissolved in water. They're aqueous solutions. And we tend to think of the thing being dissolved as something else like salt or whatever, right, is being dissolved. So the solute is the thing being dissolved, the solvent is the thing doing the dissolving, and the solution is the homogeneous mixture. Make sure you write them down, pause the video, and do that. Alright, so how do I know which one is the solvent and the solute? Well, in the case where I'm dissolving salt in water, the salt changes state. So it changes from a solid into an aqueous solution. It dissolves. So the solute is often changing state. But in some cases, it's not changing state. So, for example, when we had our example with food coloring, the food coloring was a liquid to start. It's still a liquid when we're done. So if neither one changes state, the solvent is the one that's in greater abundance, meaning we have more water than we have food coloring. So the water is the solvent, and the food coloring is the solute. Now, when you look at something like Dr. Pepper, you'll notice, and unfortunately I'm doing this red on red, but notice up here carbonated water is the #1 ingredient. That means it is the most prevalent. That is the thing that is the solvent, and everything else in here is a solute, meaning it is dissolved in the water. So the high fructose corn syrup is dissolved in water. The color is dissolved in water. The phosphoric acid is dissolved in water, etc. All of these are dissolved in water. Okay, so here is a salt solution that we're starting to mix up. We put a bunch of salt in it, we've stirred it around, etc. We have the concept of solvation. So again, pause the video and write down what solvation means. It is the process by which the positive and negative ions of an ionic solid become surrounded by solvent molecules. So you have to think about what's going on at the molecular level. And we'll see this in just a second. So pause the video, write that down. Alright, remember salt is a crystal and it's being ripped apart by the water. And that's exactly what solvation is. So we're going to give you an example. Think of the Wizard of Oz. If you've seen the Wizard of Oz, you've seen Dorothy and her friends all on their way to see the wizard, and they're all very happy together, and they're walking down the yellow brick road, etc., and they walk into the forest, and they are accosted by a bunch full of monkeys. Okay, and the monkeys go and tear everybody apart, and break everybody apart, and grab Dorothy, and whisk Dorothy off to the witch's castle. All right. So what we've actually done is we have taken a group of people who are all very happy together and ripped them apart. That's exactly what's happening with salt. Now, if we look at salt over here and we look at the green one, as the green ones are going to be chlorine because they're bigger, they're negative, and the sodiums are positive, they're very happy over here in a crystal. Okay? And what happens is water comes along and hits the crystal. And it starts to dissolve the crystal. And the way it dissolves the crystal is the water has a positive and a negative end, and the negative end of the water gets near the sodium, and another water comes over, and another water comes over, and they start to rip apart at the sodium and they pull it away. So eventually what happens is the sodium is over here, and it's surrounded by a bunch of water molecules with all the negative parts of the water molecules facing the sodium. Similarly, when you have chlorine, the hydrogen, which is positive, the hydrogen parts of the molecule of the water molecule are close to the chlorine, and they've ripped it apart. Right? So over time what happens is more and more salt goes into the water, so you end up with bunches and bunches of salt dissolved in the water. And again, when you get it dissolved, the chlorine ions, which are negative, are surrounded by waters, and the positive sodiums, which are over here, the sodium ions, are also surrounded by water. Right? What we're going to do is see if we can manage to get to this link. For a second, I need to do, that's not where I want to be. I want to do Control A and click on salt dissolving. And let's see what happens. Great. So we're going to start this little movie, and in the example, salt is added to water. Right, so we see the salt. The water is acting as the solvent, and the salt is acting as the solute. So what's happening is the water comes around, and the negative oxygens surround the positive sodiums and rip it apart. Similarly, the positive ends of the water molecules surround the chlorine and rip it off, etc., etc. So the salt molecule, the salt, it's not a molecule, the salt compound, the crystal of salt, is ripped apart. Okay? So as the water molecules surround each ion, a hydration shell is formed around them, meaning it's water. Right? So there's a shell that's around the chlorine ion, and there's a shell that's around the sodium ion, so that they do not touch each other and they do not recombine. Right? Now why is that? It's because chlorine is extremely negative, and it's more attractive to the water than the other water molecules are. So the hydrogens are very much attracted to the chlorine. Similarly over here, the oxygens are far more attracted to the sodium than they are to the hydrogens of other waters. So as a result, they get much, much closer. They hold the sodium and rip it apart from the chlorine. Okay? Come on. Done. Go back here. Cool. All right. All right. So we need to write some more terms down, so pause the video and write these down. Soluble, something is soluble if it will dissolve, if the solute will dissolve in the solvent. It's insoluble if it will not dissolve in the other substance. Okay? So salt, for example, will dissolve in water, but it will not dissolve in gasoline, for example. All right, we also have a bunch of properties of water. Now, water covers about 70% of our Earth, and it has some special and some often unique properties that you need to be aware of. Right? Remember that water is what we consider an aqueous solution. Aqua means water, so these are aqueous solutions. And you have to remember that a solution is a homogeneous mixture, it looks like one thing, of a solute and water. The solvent is always water in an aqueous solution. So you need to remember that. Now, when we look at water, one of those unique properties that water has is it has something called surface tension. So as you look at this leaf, you see that we have this water droplet on the leaf. And all of the water droplets are pretty round. All right? So we notice that for some reason, water droplets are round. Why is that? Why does water end up getting round? All right? Well, there's a very good reason. It's something called surface tension. And we have water molecules. Let's look at a particular water molecule. Right? And we have this water molecule that's labeled up here as number 1. And we have a water molecule in here. All right? And we have a water molecule out here. Now, all of these water molecules are attracted to each other. The positively charged hydrogen is attracted to the negatively charged or slightly negatively charged oxygen. So they attract each other. We call these things right here hydrogen bonds. And we've covered this in a previous podcast, but just kind of bring it back into your mind. These are called hydrogen bonds. They are not actually bonds. They are simply attractive forces. But what happens on the surface of a liquid, specifically on the surface of water, is it creates all of these bonds to other hydrogens, all of these other attractive forces between the hydrogens, between one molecule, that's one molecule of water, and other molecules of water. And so as a result, they line up and they create this nice surface and pull together. And they hold together the surface of the liquid. And that's why it turns into a drop. Right? If you go and you take a penny and you put drops of water on it, you will notice that this water, you can put a lot more on top of this penny than you think you can, right? Because the water all holds together. It doesn't just pour off the side, which is what you might expect. Now, if you try this with alcohol or gasoline or something else, it's going to pour right off the side. Oil, something like that. It's just going to get to the side of the penny and just pour right off. Water doesn't do that. It creates this almost a bubble-like appearance on top of the penny, right? And that's because of the surface tension of the water. This is the reason that certain bugs, this is a skeeter bug, also known as a water bug, it can walk on top of water. And if you go out to a place like Smith Mountain Lake early in the morning this summer, you will find that you can see these things walking on top of the water, and they don't sink. And the reason they don't sink is because of the surface tension that's on top of the water. If you go into space and you just take water and you just let it sit there freely in space, like inside a spaceship, it has to have air around it, it'll just become a ball of water, just like this. So I'm going to show you this cool little video of a guy who goes and he tries to drink water in space. So it's kind of cool when he tries to drink water in space. This is actually an astronaut. This is done in space, right? So he sits there and there's this glob of water sitting in the air, and he goes and he sucks it right in and drinks it. If you actually watch him when he does that, you can actually see him swallowing as he's pulling it in. Right? So he's just going and taking this water, which is just sitting there in space, and you'll notice that it all holds together. It doesn't break apart. And it's holding together because of the surface tension on the surface of the water that all holds it together. Okay. All right. So here's our water, and we talked about it has surface tension because of this hydrogen bonding. Remember, and I've said it many times before, but I want to say it again, that this is not actually a bond, it's simply an attractive force between molecules. So molecules without a large number of hydrogen bonds do not do this. Water does this because, if you remember, we talked about what a hydrogen bond was, and it's generated by a very strong dipole, where it has to be a bond between hydrogen and oxygen, or hydrogen and nitrogen, or hydrogen and fluorine. And they will create very, very polar molecules that will allow hydrogen bonding to happen. Now, this does not happen with gasoline. It does not happen with alcohol. All right, so This does happen with water. That's why we said water is very unique, right? Because it has an extremely high surface tension. Okay. Now, how do we ruin surface tension? Well, we have something called a surfactant, right? And you should write down the word surfactant, and you should write down its definition. And a surfactant is any substance that interferes with the hydrogen bonding between water molecules, thereby reducing surface tension. So, can you think of something that might be a surfactant? Well, I'll bet you can. One of the most common is something like Dawn dishwashing liquid. You put some Dawn dishwashing liquid or some soap on top of this penny, the water won't do this, right? Because the surfactant is going to go and completely destroy the surface tension. Okay. All right. Please go off and do the worksheet. Please learn these terms. We're going to be using these terms in future podcasts, so make sure you understand them, especially things like solution, solubility, solvent, solute, solvation, those kinds of things, because we're going to use them a lot. Okay? Thanks a lot. Have a great day. We'll see you in class if you have questions. Take care. Bye.